So far, relations have just consisted of pairs. Now let's think about a little bit where the two halves of the pairs come from. The domain of a relation consists of all possible values of x, that is, the first entry in the pairs. So, for example, if R is the relation consisting of the four pairs 3, 1, 2, 5, 3, 4, and 5, 1, well then its domain, which we write DOMR, is 3 appears here as the first entry in a pair. Here's 2. Here's 3, but we don't need to repeat ourselves. And here's 5. The domain consists of just the three numbers 3, 2, and 5. And when we're describing a collection like this, we don't need to repeat ourselves, and order doesn't matter. So we just wrote 3, 2, 5, not 3, 2, 3, 5. We could, if we felt like it, also write 2, 3, 5, or any other arrangement of our elements that we wanted, as long as those three numbers are all there. All right, what if we have a function that's given in one of the other forms that we've met? Let's suppose that S is the relation graphed here in purple, and we want to find the domain of S. The domain is all of the possible values that x might take. So we imagine taking this graph and squishing it into the x-axis. So in this picture, what happens when we do that? Right, we have bits of the graph above and below the x-axis from -4 all the way up to 4. So in set builder notation, we could say the domain of S is the collection of all numbers x such that, what's the condition? Well, x has to be between -4 and 4. Equals is included, right? Because it touches this point with x-coordinate -4. It touches this point with x-coordinate +4. Now there's another way to express this set. We could express this set in so-called interval notation as square bracket -4 +4 square bracket. Let's take a minute and review interval notation. Square bracket, because we have a less than or equals at the left end, right? -4 is less than or equal to x. If it were just less than, we would have a round bracket, which is the thing that looks like this. Same thing here. We have a square bracket over here because its x is less than or equal to 4. If it were x is less than 4, we would have a round bracket going in the other direction, of course. What are these numbers? Well, this is the smallest value we want to describe, and this is the largest value. They have to be given in this order, smallest then largest. We'll talk a little bit more about interval notation in a later video. For now, let's take a look at another domain. Let's let T be the relation graphed in black here. I'm going to have you pause the video and try to find its domain. Remember, to find the domain, just imagine squishing the graph into the x-axis. Pause the video and try it now. Okay, so again, it looks like the far right end is over here. The far left end is over here. And there aren't any gaps in the middle. So it looks like if we squish this into the x-axis, it'll look something like this. We've got -3 is our left end. And then 4 is our right end. In interval notation, we can write that as -3, 4. Again, square bracket, because the ends are included. What about when we have a relation that's described using an equation? Well, when we have a relation described with an equation, we think about what values of x would work in the equation. And we don't have very many examples of equations that we know how to work with so far. One example, we might consider the relation all xy so that 2x plus 4y equals 9. Well, you know, I could plug in any x that I wanted here and then find a y to go with it. Right? Just subtract off this number and then divide by 4 to find the y. No matter what x I plug in, I can always find a y to go with it and work in this equation. So with this equation, every number works. How do we describe that? Right, well, we say that the domain of R is all real numbers. Or we could use the name of the set of real numbers, which is this Blackboard caps R. This just means if you've seen this symbol before, you may use it. If you've never seen this symbol before, be aware that I may use this to refer to the set of all real numbers. Or if we want to write this in interval notation, there's no smallest x that works. So we write round bracket -infinity. This whole thing, round bracket -infinity, means no smallest number, comma, positive infinity round bracket. Positive infinity round bracket means no biggest number. Right? Don't think positive infinity is a number that is the right endpoint. That's not what it is at all. This whole sequence, positive infinity round bracket, means no biggest number. We never write either kind of infinity with a square bracket. We always write negative infinity as a left endpoint. It can't be a right endpoint. We always write positive infinity as a right endpoint. It can't be a left endpoint. Right, so it's easiest if you think of this whole thing as one symbol that just means there's no smallest thing. This whole thing is one symbol that just means there's no biggest thing. Any of these three ways of writing all real numbers is correct. Right, so let's see an example where some numbers don't work. Let S be the relation where x is related to y when x equals y squared. Right, well, when we square a number, when we square a negative number, we get a positive number. When we square a positive number, we get a positive number. When we square 0, we just get 0. Right, so y squared is always greater than or equal to 0. Right, which means x has to be greater than or equal to 0. Thus, the domain of S is the set of all x such that x is greater than or equal to 0. If we wanted to write that in interval notation, right, 0 is allowed. Its x is greater than or equal to 0. So we'll have square bracket 0. But that's the smallest thing. Is there a biggest number greater than or equal to 0? Well, no, it goes on forever. So there's no biggest number. We write positive infinity round bracket for the right endpoint.